Hello students, welcome to the lecture on decision support systems, and after this lecture we will be able to learn the following objectives. Describe problem solving and decision making, explain about Simon's model of decision making, discuss components of decision support system, explain about group decision support system GDSS. Let us discuss about decision support system. Today it is still possible to reconstruct the history of decision support systems from first-hand accounts and unpublished materials as well as published articles. This hypertext paper is a starting point in documenting the origins of the various technology threads that are converging at the start of the 21st century to provide integrated support for managers working alone, in teams, and in organization hierarchies to manage organizations and make a more rational decision. History is both a guide to future activity in this field and a record of the ideas and actions of those who have helped advance our thinking and practice. Decision support system evolved early in the era of distributed computing. The history of such system begins in about 1965, and it is important to start formalizing a record of the ideas, people, systems and technologies involved in this important area of applied information technology.
Decision support system.
A decision support system is a computer-based information system that supports business or organizational decision-making activities. DSSs serve the management, operations, and planning levels of an organization and help to make decisions, which may be rapidly changing and not easily specified in advance. Decision support systems can be either fully computerized, human, or a combination of both. DSSs include knowledge-based systems. A properly designed DSS is an interactive software-based system intended to help decision-makers compile useful information from a combination of raw data, documents, and personal knowledge, or business models to identify and solve problems and make decisions. Typical information that a decision support application might gather and present includes inventories of information assets including legacy and relational data sources, cubes, data warehouses, and data marts, comparative sales figures between one period and the next, projected revenue figures based on product sales assumptions.
History.
According to Keene, the concept of decision support has evolved from two main areas of research: the theoretical studies of organizational decision-making done at the Carnegie Institute of Technology during the late 1950s and early 1960s, and the technical work on technology in the 1960s. It is considered that the concept of DSS became an area of research of its own in the middle of the 1970s, before gaining in intensity during the 1980s. In the middle and late 1980s, Executive Information Systems (EIS), Group Decision Support Systems (GDSS), and Organizational Decision Support Systems (ODSS) evolved from the single-user and model-oriented DSS. According to Seoul 1987, the definition and scope of DSS has been migrating over the years. In the 1970s, DSS was described as a computer-based system to aid decision-making. In the late 1970s, the DSS movement started focusing on interactive computer-based systems which help decision-makers utilize databases and models to solve ill-structured problems. In the 1980s, DSS should provide systems using suitable and available technology to improve effectiveness of managerial and professional activities. In end-1980s, DSS faced a new challenge towards the design of intelligent workstations. In 1987, Texas Instruments completed development of the Gate Assignment Display System GADS for United Airlines. This decision support system is credited with significantly reducing travel delays by aiding the management of ground operations at various airports, beginning with O'Hare International Airport in Chicago and Stapleton Airport in Denver, Colorado. Beginning in about 1990, data warehousing and online analytical processing (OLAP) began broadening the realm of DSS. As the turn of the millennium approached, new web-based analytical applications were introduced. The advent of better and better reporting technologies has seen DSS start to emerge as a critical component of management design. Examples of this can be seen in the intense amount of discussion of DSS in the education environment. DSS also have a weak connection to the user interface paradigm of hypertext. Both the University of Vermont PROMIS system for medical decision-making and the Carnegie Mellon ZOGKMS system for military and business decision-making were decision support systems which also were major breakthroughs in user interface research. Furthermore, although hypertext researchers have generally been concerned with information overload, certain researchers, notably Douglas Engelbart, have been focused on decision-makers in particular. Decision generate by chronicle format. So it is important.
Taxonomies.
As with the definition, there is no universally accepted taxonomy of DSS either. Different authors propose different classifications. Using the relationship with the user as the criterion, Head and Schuyler differentiates passive, active, and cooperative DSS. A passive DSS is a system that aids the process of decision-making, but that cannot bring out explicit decision suggestions or solutions. An active DSS can bring out such decision suggestions or solutions. A cooperative DSS allows the decision-maker or its advisor to modify, complete, or refine the decision suggestions provided by the system, before sending them back to the system for validation. The system again improves, completes, and refines the suggestions of the decision-maker and sends them back to him for validation. The whole process then starts again, until a consolidated solution is generated. Another taxonomy for DSS has been created by Daniel Power. Using the mode of assistance as the criterion, Power differentiates communication-driven DSS, data-driven DSS, document-driven DSS, knowledge-driven DSS, and model-driven DSS. A communication-driven DSS supports more than one person working on a shared task. Examples include integrated tools like Microsoft's NetMeeting or Groove. A data-driven DSS or data-oriented DSS emphasizes access to and manipulation of a time series of internal company data and, sometimes, external data. A document-driven DSS manages, retrieves, and manipulates unstructured information in a variety of electronic formats. A knowledge-driven DSS provides specialized problem-solving expertise stored as facts, rules, procedures, or in similar structures. A model-driven DSS emphasizes access to and manipulation of a statistical, financial, optimization, or simulation model. Model-driven DSS use data and parameters provided by users to assist decision-makers in analyzing a situation. They are not necessarily data-intensive. Dicadus is an example of an open-source model-driven DSS generator. Using scope as the criterion, Power differentiates enterprise-wide DSS and desktop DSS. An enterprise-wide DSS is linked to large data warehouses and serves many managers in the company. A desktop, single-user DSS is a small system that runs on an individual manager's PC.
Components.
3 fundamental components of a DSS architecture are the database or knowledge base, the model that is, the decision context and user criteria, and the user interface. The users themselves are also important components of the architecture.
Development frameworks.
DSS systems are not entirely different from other systems and require a structured approach. Such a framework includes people, technology, and the development approach. DSS technology levels of hardware and software may include the actual application that will be used by the user. This is the part of the application that allows the decision-maker to make decisions in a particular problem area. The user can act upon that particular problem. Generator contains hardware-software environment that allows people to easily develop specific DSS applications. This level makes use of case tools or systems such as Crystal, Analytica and I Think. Tools include lower-level hardware-software. DSS generators including special languages, function libraries and linking modules. An iterative developmental approach allows for the DSS to be changed and redesigned at various intervals. Once the system is designed, it will need to be tested and revised where necessary for the desired outcome.
Classification.
There are several ways to classify DSS applications. Not every DSS fits neatly into one of the categories, but may be a mix of two or more architectures. Holsable and Winston classify DSS into the following 6 frameworks: text-oriented DSS, database-oriented DSS, spreadsheet-oriented DSS, solver-oriented DSS, rule-oriented DSS, and compound DSS. A compound DSS is the most popular classification for a DSS. It is a hybrid system that includes 2 or more of the 5 basic structures described by Holsable and Winston. The support given by DSS can be separated into 3 distinct, interrelated categories: personal support, group support, and organizational support. DSS components may be classified as inputs, factors, numbers, and characteristics to analyze, user knowledge and expertise, inputs requiring manual analysis by the user, outputs, transform data from which DSS decisions are generated, decisions, results generated by the DSS based on user criteria. DSSs which perform selected cognitive decision-making functions and are based on artificial intelligence or intelligent agents technologies are called Intelligent Decision Support Systems (IDSS). The nascent field of decision engineering treats the decision itself as an engineered object, and applies engineering principles such as design and quality assurance to an explicit representation of the elements that make up a decision.
Decision support systems are gaining an increased popularity in various domains, including business, engineering, the military, and medicine. They are especially valuable in situations in which the amount of available information is prohibitive for the intuition of an unaided human decision maker and in which precision and optimality are of importance. Decision support system can aid human cognitive decencies by integrating various sources of information, providing intelligent access to relevant knowledge, and aiding the process of structuring decision. They can also support choice among well-defined alternatives and build on formal approaches such as the methods of engineering, economics, operations, research, statistics, and decision theory. They can also employ artificial intelligence methods to address heuristically problems that are intractable by formal techniques. Proper application of decision-making tools increases productivity, efficiency, and activeness and gives many businesses a comparative advantage over their competitors, allowing them to make optimal choices for technological processes and the parameters, planning business operation, logistic, or investment. Now we will discuss about problem solving and making. Problem solving is a process in which we perceive and resolve a gap between a present situation and a desired goal, with the path to the goal blocked by known or unknown obstacles. The steps in both problem solving and decision making are quite similar. In fact, the terms are sometimes used interchangeably. Most models of problem solving and decision making include at least 4 phases. An input phase in which a problem is perceived and an attempt is made to understand a situation or problem, a processing phase in which alternatives are generated and evaluated and a solution is selected, an output phase which includes planning for and implementing this solution, and a review phase in which the solution is evaluated and modifications are made if necessary. Most researchers describe the problem-solving or decision-making process as beginning with the perception of a gap and ending with the implementation and evaluation of a solution to fill that gap.
Problem-solving and decision-making. So one of the overall models or processes that we can follow for decision-making would be Kepner-Tregoe. And you can start with situational analysis. What is the current situation in the present time? So you would collect data, ask questions, try to be objective, break the problem down into different components so you can figure out what's going on. Then you would move to step 2, problem analysis. So you're developing like probable causes of the problem, and you might test and see what's true, identify the most likely causes, and then you would move to the 3rd step, where you would try to make a decision on how you would change the current situation to solve the problem. And this is basically the process you would follow: situational analysis, problem analysis, and then decision analysis. And another really good approach to problem solving is the scientific approach to problem solving. This is what scientists use. They start by asking questions. They observe what's changed, and they start asking, well, why has it changed? And they define problems in terms of questions. And next they would conduct research on the issue. They would collect data, take samples, make comparisons. And from this research, they'll take their best guess as to what's the cause. And this best guess takes the form of a testable and measurable statement known as a hypothesis. And they will test that to see what's true or false. They'll analyze those results, and they'll report those results to their peers so people can critique it. So this is a really good validation, airtight model for problem solving. And as it relates to investment decision making, you'll find that major investments will go through certain feasibilities or toll gates throughout the life cycle of the investment, especially up front when you make the initial investment. You'll have some aggressive feasibility studies and analysis that you'll go through, such as maybe operational feasibilities. Do people and the users agree with it? Do they buy into the investment decision that you're making? The economic feasibility may conduct cost-benefit analysis to see exactly, is it financially feasible? And then technical feasibility, do you have the technical expertise and capabilities to pull off the investment? So you may go through a lot of different feasibilities before you actually make the investment itself. Then one of the important concepts we covered in this course was critical thinking. I mean, the world is changing rapidly. You have information overload. You got more complexity. Things are connected globally and much more interdependent. So what's happened is critical thinking is becoming extremely important. And at the heart of critical thinking is your ability to reason and work through an issue, so you're searching for what's true and false. You know how to think through a problem objectively and in a fair-minded way. Critical thinking is really quality thinking. And just think about like what critical thinking is not. I mean, people who sometimes act emotionally on gut feelings, they have no real basis for making decisions. They tend to be somewhat gullible. I mean, people who are critical thinkers are very skeptical. They want proof before they just accept things. So contrast this between how people think non-critically, where they hold on to traditional viewpoints despite what the evidence shows them. And then the other half of the coin, or the other side of thinking besides critical thinking that we really need to understand, would be creative thinking. And there's a book called A Whole New Mind. It was written by Daniel Pink, and he really pointed out vividly how we as a society and people need to move towards creative type thinking, because we live in a world of abundance. And with so much abundance around us, we have to become more unique to stand out and be competitive, and that requires more and more creative thinking. And this process is not easy. It takes a lot of hard work. We gave a good example of this in the course on the Wright brothers, if you can recall that. And another way to kind of understand it is you can kind of think of creative processes extend over very long periods of time. It's like the Wright brothers, they invented the airplane initially, but it was very crude. So it emerged over a long period of time to improve and get better and better. So a lot of innovation and creative thinking takes place through hard work, a lot of testing, and it takes a lot of time sometimes to get from point A to point B. It's not a quick process necessarily. And then we can kind of bring these two together in a nice process. If you want to think of it, you might say we flow from right to left. So we need to generate a bunch of new ideas. So we need a lot of these right brain, creative thinking kind of people to kind of come into the room and do what we call divergent, generate a lot of ideas. And then once we've got all those ideas, we want to get the critical left brain kind of thinking in place so that we can get down to what is exactly the good idea or the best idea. That's kind of a nice way to look at the two and within a single process. And then if we want to get even more accurate and precise in managing thinking styles, we can actually divide it into 4 quadrants. And there's a very good measurement tool to assess this, and it's called the Herman Brain Dominance Instrument. And when you understand thinking styles, you can really zero in on how to use your people really well. For example, a very analytical person would be in quadrant A. They're very logical thinkers. They can cut through the detail, get rid of ambiguity, give you the bottom line answer. A person in the B quadrant would be real good at writing procedures, following orders, prefers a lot of structure to a process. Then if you want someone with good personal skills and deals with people, then you would want to go to quadrant C. And then the quadrant D person would be a lot more imaginative, creative, holistic in their thinking.
Although each group of decision is specific in domain and time demandingness, we can find common principles and tools for making better decisions. Any manager can use the following techniques to overcome the barriers to effective decision making. Increased knowledge. A lack of experience with the problem at hand can cause anyone to make poor decision. De-biased judgment. De-biasing judgment requires 4 steps. Understand that the possibility of bias exists. Understand how bias can affect judgment. Analyze previous decisions to determine how bias may have affected them, and accept that while biases exist, they can be minimized through diligence. Be creative. Creativity is the process of developing original, novel responses to a problem. It is essential for decision-making activities such as discovering alternatives or defining problems. Use intuition. Intuition can be defined as a cognitive process whereby we consciously make a decision based on accumulated knowledge and experience. Don't overstress the finality of the decision. Very few decisions are forever. There is more give in decision than we realize. Make sure the timing is right. Managers should not let their decision be swept by passing moods. Decision making is selecting a course of action from among available alternatives. Process of analyzing critical data to determine the best decision. We do not always select the best choice when faced with alternatives. Need a rational, systematic and effective approach for deciding on a course of action. Organizing has limited resources, that is number of employees, time, money, etc. and those limits require managers and supervisors to make choices. Problem solving involves defining a problem and creating solution for it. Decision making is selecting a course of action from among available alternatives. Problem solving, step 1 to 4, always involves decision making, step 3. However, not all decision making involves solving a problem. For example, a supervisor may have to make decisions about employees, resources, workload, etc. without having a problem to solve. Let us discuss about Simon's model of decision making. A communication-driven GDSS supports more than one person working on a shared task. Many collaborators work together to come up with a series of decisions to set in motion a solution or strategy. Most communication-driven GDSS are targeted at internal teams, including partners. The most common technology used to deploy the GDSS is a web or a client server. In general, groupware, bulletin boards, audio and video conferencing are the primary technologies for communication-driven decision support. Data-driven GDSS model puts its emphasis on collected data that is then manipulated to fit the decision maker's needs. This data can be internal, external, and in a variety of formats. This model emphasizes access to manipulation of a time series of internal company data and sometimes external and real-time data. Simple file system access by query and retrieval tools provide the most elementary level of functionality. Apparently, Kepner-Tregoe and Tolove were the first to use the notion of evolution in Decision Support System (DSS). Soon after that, Kane elaborated on key aspects related to evaluation in DSS. That research was most concerned with the notion that DSS evolved over time. The development methodology of DSS is an evolutionary one. In a closely related set of developments, Lehman et al. Appear to have been the first to use the term evolution in conjunction with generic computer software. In particular, Lehman labeled software development and maintenance as software evolution. He described software change and enhancement as unending, suggesting that evolution also is unending. DSS as a bundle of hardware, data and knowledge, user interface and software application change and evolve over time. As a result, the purpose of this paper is to investigate the notion of DSS evolution and DSS characteristic and component evolution. Previous literature has primarily been concerned about the notion that DSS evolved and that methodologies of DSS development consider that evolution. In addition, there has been some concern as to why DSS evolved. However, there has been limited research according to how DSS actually changed and evolved over time. Accordingly, we review the previous literature on DSS evolution according to its individual components and provide specificity for DSS evolution through those components changing over time. In addition, we extend the notion of evolution to a more proactive perspective, aim at managing of evolution, where we try to predict and facilitate evolution as part of DSS management rather than just passive evolution. In general, evolution does not mean that what was previously processed historically will continue to be processed in the same manner. That is, backward compatibilities, artifacts such as taxonomies and knowledge bases and general are not backward compatible. They evolve to solve the problem as a user problem and capabilities change. Further, as noted above, users may change so that even users are not backward compatible. As a result, typically a problem of interest at time is not necessarily of interest at time t+1 and not necessarily solvable with the same DSS to derive the same solution. There are at least two distinct features associated with DSS evolution. Beyond knowing that it will occur, prediction of what the system will evolve to and facilitation of that evolution. Predicting evolution has to do with trying to understand what future states or states the current system will evolve towards. Facilitation has to do with trying to understand how to best push or change the system to a new future state. As a result, facilitation may include identification of a particular future state for the system to evolve to. In machines, we can formally plan for evolution of the overall system and particular system aspects. As a result, in that setting, evolution is a formal process, typically with particular observable end state or intermediary state. Generally, the formal aspect of evolution is associated with the formal evolution of individual components, example database evolution, aim at plant and states. However, evolution is not necessarily a formal process. In classic DSS evolution, example Keene 1980, there is an air of informal evolution in that setting evolution can result from informal or non-planned changes that occur over time. Emergent system properties are those properties that result from using the system and from system components interacting with each other. Individual components would not exhibit the behavior. Instead, it is with the interaction of the components that the behavior arises. Because of the interaction, behavior evolves. In general, emergent properties are not always predictable. Instead, they are a function of the interaction and evolution of the components. Emergent properties are likely to be less predictable and possibly less visible than other system properties. As a result, determination of the extent of evolution typically will depend on change in DSS artifacts. Those artifacts can either be an explicit part of the system or ancillary to the system. Artifacts embedded in the DSS might include database, schema, or taxonomies. Comparing artifacts at particular points in time will allow us to gauge the extent of evolution. Since the analysis is based on particular artifacts, much of the analysis is likely to be artifact-specific. The fact that DSS evolved, and including that evolutions in the development methodology associated with DSS, has been apparent from the beginning of DSS. Historically, Kent was most concerned with the notion that system actually evolved and what seemed to cause that evolution. Evolution was built into the notion of how DSS developed over time. When Kent discussed the concept of evolution, he directly indicated that the final system can be developed only through a process of learning and evolution, and that the DSS evolves in response to learning. Kent felt that evolution occurred only because of interaction between user and designer, learning, personalized use, or the evolution of new function. He also indicated that the system evolves in response to evolving needs. Kent indicated that program structures and programming methods need to facilitate evolution. Kent indicated that evolution means adding new commands that probably would be translated as adding new capabilities, but did not provide further guidance as to how to actually evolve DSS. Kent did suggest that there is a need to study the evolution of data and data structures, and that data-based DSS do not evolve as easily as model-based DSS. Kent also saw evolution as technology-based, since he noted that evolution can be blocked by the inability to obtain additional technology. Finally, he noted that complex systems evolve from simple systems. The data management component performs the function of storing and maintaining the information that we want our decision support system to use. The data management component, therefore, consists of both the decision support system information and the decision support system database management system. The information we use in our decision support system comes from one or more of three sources: organizational information. We may want to use virtually any information available in the organization for our decision support system. What we use, of course, depends on what we need and whether it is available. We can design our decision support system to access this information directly from our company's database. Some decisions require input from external sources of information. Various branches of federal government, Dow Jones, composite data, and the internet, to mention just a few, can provide additional information for the use with a decision support system. Personal information: we can incorporate our own insights and experience, our personal information, into our decision support system. We can design our decision support system so that we enter this personal information only as needed, or we can keep the information in a personal database that is accessible by the decision support system. The model management component consists of both the decision support system models and the decision support system model management system. A model is a representation of some event, fact, or situation. As it is not always practical or wise to experiment with reality, people build models and use them for experimentation. Models can take various forms. Decision support system help in various decision-making situations by utilizing models that allow us to analyze information in many different ways. Models we use in a decision support system depend on the decision we are making and consequently the kind of analysis we require. For example, we would use what-if analysis to see what effect the change of one or more variables will have on other variables, or optimization to find the most profitable solution given operating restriction and limited resources. Spreadsheet software such as Excel can be used as a decision support system for what-if analysis. The user interface management component allows us to communicate with the decision support system. It consists of the user interface management system. This is the component that allows us to combine our know-how with the storage and processing capabilities of the computer. To accomplish these goals, it uses a decision support system which performs three tasks. Data management. The decision support system stores customer and product information. In addition to this organizational information, lands and also needs external information such as demographic information and industry and style trend information. Model management. The decision support system has to have models to analyze the information. The models create new information that decision makers need to plan product lines and inventory levels. For example, lands and uses a statistical model called regression analysis to determine trends in customer buying patterns and forecasting models to predict sales levels. User interface management. A user interface enables lands and decision makers to access information and to specify the models they want to use to create the information they need. Knowledge management component, like that in an export system, provides information about the relationship among data that is too complex for a database to represent. It consists of rules that can constrain possible solution as well as alternative solution and methods for evaluating them. According to Malach, GDSS architecture should define and specify the following components. Database or databases including any existing databases, internal or external to the organization, and any databases that are created specifically for DSS use. The architecture schematic should identify who is responsible for different types of databases including their accuracy, currency, and security. Model or models, including information about their sources of data, processing, the organizational unit, responsibility for maintaining them, and limits on access to them. Software tools for users to access the database and the models, and software tools which system administrators can use to manage the database and the models. Hardware and operating system platforms on which the databases and models resides, on which the programs run, and through which a user access the DSS. Any constraints such as a policy to standardize on products of a particular vendor or products that use a particular operating system should be stated. Networking and communication capabilities needed to connect the hardware platforms. These capabilities must support needs to connect to one or more servers and databases, needs of work group members to communicate within the group, and enterprise needs to link work groups to each other or to share data. DSS, whose design structure and uses reflect the way in which members of a group interact to make a particular decision or type of decision. Supports group decision processes, communication, file sharing, and modeling of group activities that involve group interaction. Example, choosing a factory layout, a group of factory managers, stockroom supervisor, shipping supervisor, assembly supervisor, paint room supervisor, milling supervisor got together to choose a factory layout. Integrated the business tasks by considering the business processes as a whole. Incorporate different perspectives into the decision process. The goal of GDSS is to improve the productivity of decision-making meetings either by speeding up the decision-making process or by improving the quality of the resulting decision, or both. This is accomplished by providing support for the exchange of ideas, opinions, and preferences within the group. Supporting parallel processing of information and idea generation by participants. 96. Decision support system enabling larger group with more complete information, knowledge, and skills to participate in the same meeting. Permitting the group to use structured or unstructured techniques and methods of arriving at decision. Offering rapid and easy access to external information. Allowing no sequential computer discussion. Unlike oral discussion, computer discussion do not have to be serial or sequential. Producing instant anonymous voting result, providing structure to the planning process which keeps the group on track, enabling several users to interact simultaneously, automatically recording all information that passes through the system for future analysis. It develops organization memory. A ESS or DSS more in general is a software system under control of one of many decision makers that exists in the activity of decision making by providing an organized set of tools intended to impart structure to portions of the decision making situation and to improve the ultimate effectiveness of the decision outcome. Sharing the same concept of a DSS and ESS focuses more in the end user requirements of maximum interactivity and user friendliness, and ESS can be understood as a friendly, fully customized and interactive DSS to be mostly used by top executives and policy makers to get permanent and updated assessment in relation to key question information and knowledge. Imagine a piece of software that runs on our PC which provides the same sort of interaction and advice as a career counselor, helping us decide what education field to go into and perhaps what course to pursue. Now, in the end, let us summarize what we have learned in this lecture. Making decisions concerning complex systems, example the management of organizational operation, industrial processes or investment portfolios, the command and control of military units, or the control of nuclear power plants often strains cognitive capabilities. Decision support systems are gaining an increased popularity in various domains, including business, engineering, the military, and medicine. Problem solving is a process in which we perceive and resolve a gap between a present situation and a desired goal, with the path to the goal blocked by known or unknown obstacles. Decision making is a process of developing and analyzing alternatives to make a decision, a choice from available alternatives. Model-driven DSS are complex systems that help analyze decisions or choose between different options.